So thanks for coming. So the seminar is about an attempt to simulate some quantum gravity system on quantum processors. So recently, there is more and more evidence that quantum gravity is basically nothing more than a certain many-body quantum system. And within the current approaches to quantum gravity, we have very limited access to the dynamics or evolution of the many-body states. Okay, and this is actually a challenge. One of the possibilities to address this issue is developed here in Krakow in the context of CDT, causal dynamical triangulations, performing numerical computations, employing classical computers, classical supercomputers. But actually simulating quantum mechanics with classical computers is challenging. So because of the recent progress in quantum computing technologies, I decided to look at the possibility of using quantum computers to simulate certain quantum models of quantum gravity. And basically I will focus on reviewing results from my recent papers, which has been put on arXiv last month. And the paper is about an attempt to perform certain kind of evaluations, namely the so-called vertex amplitudes, which are elementary quantum processes in loop quantum gravity, using available quantum computers. So the first thing to stress is that quantum computers are not science fiction anymore. They do exist, not only in physical laboratories, but actually there are first commercial machines available. In my studies, I'm going to focus on the IBM quantum computer, specifically 5-qubit quantum computer, which is as I will explain you in a second, is available online. But there's, of course, much more. Another class of quantum computers are the so-called quantum annealers. I was discussing the application of quantum annealers to simulate certain quantum gravity systems this autumn, actually, this spring, sorry. And but there is much more. There is, for instance, Rigetti quantum computer, which is under preparation at the moment, and they claim that they will release 128 qubit universal quantum computer with a certain type of interconnection between the qubit next year. All of these initiatives are either American, US or Canadian as D-Wave. But hopefully Europe does want to be a loser in this game as well, okay? And recently the quantum flagship, the third European flagship research project, has been launched. 2 or 3 weeks ago in Vienna there was a kickoff for the event. So we had a human brain project, there was a graphene before, and now we have a quantum Europe. And the aim of the project is to push the quantum technologies in Europe forward, investing €1 billion within 10 years. And 2 weeks or 3 weeks ago, actually, the first part of the money was distributed among over 20 research groups. More than 100 million euros was distributed, and one of the projects, I think, which got something like 20 million euros, is devoted to construction of European quantum computers with 100 qubits around. Okay, so In Europe, we can expect also development of the quantum computing technologies with around 100 qubits within the next, I would say, 4 or 5 years. But I mean, if you would take a look at the history of quantum computers, I think the first quantum computers that I heard about was the molecular one in 2001, which I read about in Scientific American when I was still in high school. And this was something very inaccessible. It was 18 or 17 years ago. And people started to push this technology forward, but there were difficulties to preserve the coherence of the quantum state. And then people devoted to development of the so-called superconducting qubits. And all of the solutions that I presented, that I mentioned, are based on the superconducting qubits. And this superconducting qubits have been proven to be a scalable solution, and it's I mean, all the noises and decoherence processes can be kept under control. And the basic idea of the superconducting circuits is very simple. And a very simplified way to explain is that you take a loop, a single coil made of superconductor. And then you know that if you have a superconductor, the magnetic flux across the superconductor is quantized due to the Masonry effect. And then there is actually nonlinearity in the structure of the levels of the quantized magnetic flux. And the two states, the two first states, namely the elementary excitation in one direction and in the other, can be used as a basis for qubit, okay? So this is something conceptually very simple. So you have these two ground and first excited states, which are used to encode the two-dimensional quantum system, which is the quantum qubit. And then you use some auxiliary circuits to prepare the state, to measure this, to perform measurements. The states basically they based on squids, very sensitive magnetometers. And this is an example of the chip provided by IBM, which is based on this superconducting circuits, superconducting qubits. And what is important is that these chips not only exist, but they are accessible. So every one of you can log in on this website and get access to this 5-qubit quantum computer, and you can start playing with this. What is important to stress is that for this 5-qubit quantum computer, not all the qubits are interconnected. There is a certain graph which represents interconnections. Therefore, there are some limits on the types of the gates that you can encode. This is 5-qubit quantum computer provided by IBM, but there is also 20-qubit quantum computer provided, but you have to pay for this. And a simple thing to do when you log into IBM website is that you have a panel with the 5 lines. It's very similar to composing music. Actually, you have some notes which are quantum gates, and you drag and drop the gates. You can use the single qubits gates, you can use 2 qubits gates, and it will be relevant for the further discussion to introduce a Bell state, one of the Bell states, namely the singlet of 2 1/2 particles. So you can create the singlet of 2 1/2 particles using the quantum chip very easily. Let's take the 2 qubits. Let's act on both of them with the so-called bit flip operations. The bit flip operations are basically the X Pauli matrices, and then you act on one of the qubits with the Hadamard gate. The Hadamard gate introduces superposition with the equal weights. So if you have 0, the Hadamard transforms your state into the following superposition. If you have a 1 here, there is a minus here, okay? So this is an example of the 1 qubit gate. And then you apply the so-called C0 controlled NOT operation, which is an example of 2 qubit gate. And the action of the C0 operator, which is acting on, this is kind of operator acting on 4-dimensional Hilbert space, a product Hilbert space of 2 qubits. Let's say that you have A and B, the product, and the A remains unchanged, therefore we call it controlled qubit. And then the second qubit is A, where this sign means that this is addition modulo 2, so this is exclusive OR, okay? So when we have 0, 0, it gives you 0. When it's 0, 1, it gives you 1. 1, 0 gives you 1, and 0, 0, and 1, 1 gives you 0 as well, okay? So this is the logical operation that you can execute using this this operation. And then by very simple action of this operator, of the sequence of these 3 operators, you get this qubit state, and you can perform any measurements you like. In particular, you can perform measurements in the basis, operational basis, computational basis, sorry. And using the simulator of quantum computer, but not the quantum computer itself, you expect you expect equal, basically, probabilities. I mean, theoretically they are equal, but due to some finite steps for the simulator, you have a slight difference. But actually what you expect is that there's equal contribution from the probabilities of those 2 states. But then if you perform computations using actual quantum computer, you see that, of course, you have the contributions from the leading states, but then you also have some other contributions which you don't like to have, and those 2 contributions are due to the decoherence and the error of the gates. And these errors accumulate in the course of the algorithm, okay? Therefore, there is also an issue to optimize the algorithm such that you have the minimal number of gates, because the bigger the number of gates, there is a bigger accumulation of the errors, okay? And the contributions from the unwanted states might be significant. Of course, the current challenge is to reduce these contributions, okay? Okay, so these are some basics, and now you can ask important question: why this might be useful, and why it might be better than using classical computers. And this is quite evident when you consider quantum simulation, something I'm interested in. I'm going to simulate a system of n qubits. And the thing is that when you have a single qubit, the dimension of the Hilbert space is 2. But then if you have an n qubit, the corresponding Hilbert space is a product of the n Hilbert spaces. And we know that the dimension of this space grows exponentially with n. So the thing is that if you have, for instance, n to the 56, okay, this number is extremely huge. And to perform simulations of these quantum systems on classical computers, basically multiplying matrices, because every operator is a matrix of dimension 2 to the 56 to the 2 to the 6. This is something extremely huge. The present supercomputers, they have difficulty to multiply such matrices, okay? So the biggest quantum system, qubit system, which has been simulated so far is with around 56 qubits, okay? Just because of the enormous dimensionality of the Hilbert space. But from the other side, the companies such as IBM or Rigetti Computing are currently developing the quantum computers with 100 or even more number of qubits. So therefore, if these computers will be available, you will be able to simulate the systems that you cannot simulate using classical computers. And this is the so-called quantum supremacy. Of course, another issue, but which is not very important, I mean, from the point of the discussion that I'm going to present, is the quantum parallelism, which produces the speed up. This is related to the fact that in one operation you can evaluate a function for a huge number of values, okay? And the reduction of computational complexity of the Deutsch, Grover, and Shor algorithms based on that fact, okay? Therefore, the problems which are NP non-polynomial on the classical computers, they reduce complexity to the polynomial one on the quantum machine. This is a very famous fact. Okay, so let's say that was introduction. And now let me say a little bit about the philosophy of what I'm really going to do with quantum gravity. Okay, how I'm going to apply it to quantum gravity. So Planck scale physics is something extremely inaccessible. This is the scales which are relevant are Planck scales, and the distance is 10 to the minus 35 meters. Okay, 20 orders of magnitude below the scale of atomic nucleus. Okay. So we tried a lot, I mean, using observational data from cosmology to learn a little bit, at least about the primordial universe where quantum gravity effects might play a significant role, but this is something very difficult. So we have only very weak constraints for the moment. So basically we can honestly say that we don't have access to the Planck scale physics at the moment. And on the ground it will be, I mean, taking into account the present energy scales, TV scales. I mean, you cannot think about exploring this physics using I mean, perhaps even within the next 1,000 years. And but on the other side, if you already have some mathematics which describes your quantum gravitational degrees of freedom, you have a given theory that you build under some, assumptions, like for instance loop quantum gravity or causal dynamical triangulations. You can map the degrees of freedom of this theory into the degrees of freedom of, let's say, your quantum processor. And from the viewpoint of quantum mechanics, this is the same quantum system. I mean, in the same way as harmonic oscillator can have different physical realizations. Okay, you can use the LC circuit. Okay, you can use you can excite the light. There are very different realizations of the harmonic oscillators. So in the same way here, there are different physical systems which are realized, which actually are described by the same quantum mechanics. And if you map your quantum system into let's say, the quantum circuit, then you have a full access to every degrees of freedom. You can perform any measurements. So in the sense, you are performing experimental quantum gravity, but I would say on the analog of quantum gravitational system, okay? And this is the idea that I'm going to develop. But then the crucial question is, of course, whether the quantum gravity can be expressed in terms of the degrees of freedom which are used in the current quantum computing technologies, namely the qubits. We are heavily based on the notion of qubits, not any other quantum objects, higher dimensional or others. But I've shown in my papers that you can do it actually. And let me say a few words about loop quantum gravity, what the loop quantum gravity is. And I mean, this is a particular approach to quantum gravity developed since 30 years already. And the basic notions in loop quantum gravities are colonomies, the parallel transports of the gauge fields. So this is very similar as you have in quantum chromodynamics. Okay, actually, Ashtekar in late 80s proved that that classical theory of gravity (GR) might be expressed in terms of SU2 variables. These are so-called Ashtekar variables. And then you can perform quantization of the system in a very similar way that you introduce quantum chromodynamics on the lattice. But in case of gravity, it's a bit more difficult because you have not only gauge symmetry, but you have invariance with respect to local diffeomorphism, namely the general covariance. And this makes things much more complicated. But the basic ingredients are colonomies, the parallel transport. And then to satisfy, the first thing is satisfy the gauge invariance with respect to the SU2 group. And then we know that under the gauge transformation, the colonomy transforms at the ends of the path. Therefore, the way to construct gauge invariant objects is to close the colonomy and trace it out, such that you remove this factor originating from the gauge transformation. So this is something what I think everyone knows from QCD. But the thing is that in loop quantum gravity, it has been shown that such Hilbert space, which is spanned by the Wilson loops, is overcompleted. And then it has been shown by Carol Rovelli and Liz Mollin that you can introduce the so-called spin networks, which are certain superpositions and products of the Wilson loops, and then they span the Hilbert space of loop quantum gravity, which behaves nicely. And basically, the spin networks are graphs with the edges which are labeled by irreducible representations of our SU2 group, and there are nodes, and these nodes are associated with so-called intertwiners, which might be additional quantum numbers. And the thing is that due to the gauge invariance, is satisfied by solving the so-called Gauss constraint. Okay, so in gravity it looks like that. It's the same like basically in electrodynamics, which means that the spin, when these links meet at the node, this spin at the node has to be equal 0. Okay. So satisfying the Gauss constraint requires, this is important, that when you have, let's say, 3 links meeting at the point, at the node, you see 1/2, 1/2, and 1, and this configuration is allowed because those spins may sum up to 0. If you would have 2 here, it would not work. That spin network would not be available. And then there is important geometrical interpretation. Namely, if you have 4 valent node, this 4-valent node is considered as a dual graph to the tetrahedra. If you have, on the other hand, the 3-valent node, the 3-valent node is dual to a triangle, 2-dimensional triangle. So then you can see that the the 3-valent nodes do not carry volume element, but 4-valent nodes, they carry non-vanishing volume element. In loop quantum gravity you have area and volume operators, and then if you act with the volume operator on this node, you get a non-vanishing eigenvalue. But if you act with the volume operator on this node, you get zero eigenvalue. Okay? So if you want to construct the 3+1 theory, you have to base on 4-valent nodes. This is important. And then, how to introduce qubit based on that? Namely, as I told you, when we consider a node, the Hilbert space at the node is a product of the Hilbert spaces associated with the links. If you have the 4-valent node, 4 Hilbert spaces meet at the node. And there's a special case when all the spin labels are equal 1/2. Therefore, the Hilbert space at this node is a tensor product of the 4-qubit Hilbert space, 4 spin 1/2. And then the thing is that if you decompose this tensor product on the direct sum, there are 2 configurations in which the spins sum up to 0. So we say that there are 2 singlets for 4 spin 1/2 particles. I mean, for 2 spin 1/2 particles, you have one singlet, okay? I mean, the configuration which gives you angular momentum equals 0. But if you have 4 spins, then there are 2 such configurations. You can see it in the direct sum. Therefore, we say that the so-called invariant subspace of this intertwiner, of this node, is of dimension 2. So this basically means that there are 2 ways to combine the spins. You can take 2 pairs of spin 1/2, you either combine them to spin 0 and they merge them, or you combine them to spin 1 particle and then merge them, okay? So in this special case, when you consider the nodes which are 4-valent, and they are dual to the tetrahedra 3-simplex, and you assume that all your spin labels are corresponding to the fundamental representation of the SU2 group, then your dimensionality of the Hilbert space at the node is equal to. And I use this 2-dimensional Hilbert space as a qubit space. Okay, I will call it intertwiner qubit. So let me now construct a general intertwiner qubit. But then first thing is to define the basis states. Of course, you can define the basis in arbitrary way, basically, in the different channels. Let me consider this specific channel, which is the most convenient one, I would say. And the 0s and the 1s states are the basis states of this intertwiner qubit. How to construct them? So the first basis states is basically originating from this configuration. So you take the 2 spins, you construct 2 spin 1/2 singlets, okay? So S is a singlet state for 2 spin 1/2 particles, and then the corresponding singlet for 4 spins is just a tensor product of these 2 singlets. But then if you have the second basis state, namely this one with the 1 in the middle, then we know that there are also 3 values of the magnetic number, and therefore you have to construct this kind of superposition using the triplets for the spin 1/2, for the pairs of the spin 1/2 particles. So at the end you have these 2 states, and the general qubit state is a superposition of these 2 basis states And each of the basis state is built out of 4 spin 1/2, let's say, particles. You can also move to another, transform to another basis. An important basis is this one, in which the action of the volume operator diagonalize, and these states are eigenstates of the volume operator associated with the volume which is of the order of the Planck volume. This is something that you can calculate knowing the form of the volume operator. This is already textbook knowledge in quantum gravity. So now, having these basis states, you can consider a general qubit state, which might be, in particular, it's convenient to express it in using the angles on the Bloch sphere. And now the important task, I mean, from the viewpoint of quantum computation, is to create this intertwiner qubit state using quantum computer. Okay, this is the first task. So in quantum computers, we have a register of n qubits, and we have some initial state. Usually the initial state is a product of the 0 states for all the qubits. Okay, so this is the initial state, which is just a product state, and then you have some unitary operator, which can be expressed in terms, can be decomposed for elementary gates, and you produce some final state psi. So the first quantum circuit that I'm going to introduce now is a circuit which generates an intertwiner qubit out of 4 elementary qubits. I have general construction for this, but now I'm going to, for simplicity and limitness of time, I'm going to show you how to do it, how to generate this intertwiner qubit for the simple case of the product of 2 singlets, namely for the one of the basis states, okay? For the 0s basis states, because this is something simple. I have a general discussion of this, but for simplicity, let me discuss this 0 basis states. Just because I already introduced how to generate a Bell state, and now you know that the 2 spin 1/2 singlet is just the Bell state that I already introduced at the very beginning, and you know already how to generate this Bell state. And now this basis state 0s is just a tensor product of 2 Bell states, 2 singlets for spins, 2 spins, 1/2. So you have just 2 pairs of this, and the resulting state will be just a tensor product of the state that you get from this circuit and from this subcircuit, okay? So this is something very simple. This is how it goes when you write it as an operator, and this operator is represented by this quantum circuit. And then you can perform measurements to verify whether what you get as an outcome is in agreement with what you expect. So we expect that the final state is of this form. But in general, in quantum computing, you may expect that your state will be a superposition of all the basis states. So when you have 4 qubits, your Hilbert space is 16-dimensional. And this is an outcome from IBM Q, the chip that I introduced already. So these are the values of probabilities of the basis states, because what you are measuring actually are in the computational basis, you are performing measurements of the probabilities of the basis states. So theoretically, we expect that there are contributions only from the 4 states, namely the 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, this one and that one. Then if you use not a quantum computer but simulator of quantum computer provided by IBM, using a finite number of shots, you have something what is similar, but there is a little bit difference. But if you increase the number of shots, you actually asymptotically get the theoretical results. But then what is important are the results that you get from actual quantum machine. So you see that these contributions, which should be there, are of course significant, but there are also contributions from other states which are significant as well. Okay, this is something what is bad. You can further optimize it, actually playing with the order of gates. Namely, if you act with the X gates at the beginning, they introduce already some error, and then this error accumulates through the C node, and C node is the most noisy gate. So you can a little bit reduce these errors, actually switching this X gates at the end, because then they do not introduce. If you introduce a certain error to the gate which has more error, then this error will accumulate. So it's better to give this error, as less as possible error at the beginning, at the enter of this more noisy gates, I would say. But anyway, the general conclusion is that the results are very noisy. Okay, there is a lot of a lot of noise. If the noise would not be reduced, okay, I mean the utility of this method, I mean, will be questionable. Okay, I mean, the way to compare the predictions, the results of measurements probabilities with the theoretical results is to compute the so-called fidelity, and this fidelity for the experimental results are at the level of 70% for this case. Yes.
Collect a large sample.
Yeah, these are. I mean, the one shot take something like microseconds. Okay, these are microseconds, but then in the open access version of IBM Q computer, you can perform 128 shots at most. Okay, so you have a limit, upper limits on the number of shots. So these results were obtained by taking basically 1,000 shots. Okay, so if it's 100 here, it means that around 100 out of 1,000 experimental results were corresponding to this state. Okay, and each measurement, each evaluation of the circuit took something like around one of the order of microseconds. Okay.
And if you would be able to repeat this on professional version, these 20 qubits?
I do not have access with the full quantum computer.
What would you expect?
I mean, basically, I will show you the architecture of the 20-qubit quantum computer at the end, because I'm going to ultimately switch to the bigger version. I started with this one, but this is kind of toy example, I would say, just to start with. And the next step is to use the 20-qubit quantum computer, but then the thing is that the architecture of the interaction is very limited. Okay. And this is quite challenging things, but at the level of the subsystems, you don't expect much difference. Yes?
I suppose that in the last column you showed the mean of the results?
No, this is you may say that you count actually the number of outcomes, and you divide by the number of, so like say this is a simple mean, but yeah.
So what about standard deviation?
I mean, you can take. I mean, the thing is that when you perform the actual experiment, okay, and you want to find the distribution, you don't have full access to all this information, okay? You may perform experiment by experiment and then with single shot and then try to extract the statistical information. But in this open version, which is for free, you have some limitations on the access to the all information. Okay, this is something what is does not allow you to extract full statistical information. Okay. Okay, but that was, the first step. Actually, I'm going to make use of this, not only just to create a single qubit. Of course, this is something, but I'm going to go further and do something what is hard to do with classical computers. Okay. And the thing is that now, as already mentioned, the state of gravity, a special state of gravity, is described by spin network. Then by action of the certain operators, you can extract actually certain numbers of volumes, areas, etc. But basically the spin network describes gravitational configuration, special gravitational configuration. But then you have time evolution. And you have certain elementary process and transition amplitudes between spin network states. And the space-time extension of the spin networks are the so-called spin forms. So the spin forms are basically how the spin networks evolve in time. And let's imagine, for instance, a spin network which, let's say, a part of which is a trivalent node. And then in a course of evolution of time, these nodes decompose into 3 new nodes. So let's say we have a chunk of volume, and this chunk of volumes creates, or atom of volume, and this atom of volumes creates 3 new atoms of volume. Okay, and the structures are described by so-called 2 complexes, and there are, I mean, the points at which these edges, I would say, decompose, are called vertices. Okay. This is a specific case of 2+1 gravity, because I already explained you that when you have trivalent node, these correspond to the triangulations, okay, in 2D. And a very important concept in quantum loop quantum gravity are the so-called boundary amplitudes. This is something what mostly people in general relativity and quantum gravity consider. Maybe the thing is the following. When you have a good notion of time, you can consider transition amplitude between some initial and final state, okay? And this is how we usually do it in quantum mechanics. We consider transition amplitude from some initial to final state. We neglect what is there on the boundaries, because usually we go with the boundaries to the infinity. But then the thing is that in GR, we don't have the preferred notion of time, okay? And we have to somehow, I mean, rule out the arbitrarily introduced time parameter from the considerations. And actually what we consider are the so-called boundary amplitudes. So actually we take a state of, let's say, what we would say initial and final, but also the boundaries in general, somewhere here, and we evaluate what is the state of the boundary, and from the state of boundary we can extract everything what is inside actually. And these are so-called, this is the so-called boundary formalism of quantum amplitudes, which is adopted in loop quantum gravity, but this is much more general framework. And then the elementary amplitude is associated with the vertex. And the amplitude of vertex is basically the amplitude of the boundary of this vertex. So if you have This is quite simple, but let me draw it. In 2+1 case, you have this graph, and this is your vertex. And you want to create a boundary. To create a boundary, this discrete boundary, you associate nodes with all the links around the vertex, and you create actually a spin network which is enclosing this vertex. And this spin network is a complete graph of this kind, and each vertex is dual to the triangle. So it means that you take 4 triangles and you glue them together edge by edge such that you create a diamond shape, and this diamond shape is enclosing the vertex inside, and this shape that you get from gluing these 4 triangles is just a discrete version of sphere. Okay, this is a discretized version of S2. But then if you go to 3+1, it's a little bit more difficult, but the idea is basically the same. But then you have 1 entering and 4 outgoing vertices, and you associate the 4 nodes with this, and the complete graph that you get is a pentagram. This is why pentagrams are important in quantum gravity. Okay, so you take a pentagram graph, and every node is dual to the 3 simplex, right? So you take 5 4 simplexes, okay, 5 tetrahedra, and you glue them face by face, and what you get topologically is S3. Okay, so this is S3, but discretized version of S3. So it means that in what you are doing actually, you enclosing the vertex by the discretized version of S3. Okay, and the S3, three-dimensional generalization of 2 sphere is actually in the simplest version described by the pentagram graph. Okay. And what I'm going to do, what I did actually in the paper, how much time left, sorry? Who is controlling the time? Okay, I still have 10 minutes. Okay, that's fine. What I'm going to do is that I take this boundary graph of the vertex, because this is important issue in loop quantum gravity, because all the amplitudes might be thereafter written in terms of such elementary processes, okay? As this is similar to Feynman diagrams, I would say, okay? Then you build up the total scattering amplitude between some initial and final state out of these elementary processes, okay? Amplitudes. So these are building blocks for quantum processes. So I take the boundary of the vertex, which is the pentagram graph, with all the spin levels equal 1/2, then I have 5 intertwiner qubits. And then the thing is that to get the vertex amplitude, I have to construct the spin network state, which is actually a product state of this 5 intertwiner qubits, and evaluate the state in some, let's say, representation state. Because basically what I get here by, let's say this is the state of boundary, and evaluation of the amplitude is evaluation of this state in some representation. I call it W. So you may say that you perform this, because you want to get a number, complex number amplitude. So you have to evaluate the state in some representation like position and momentum representation. And the thing is, right now the choice of the W state, by purpose I've chosen the state to be maximally entangled state between the pairs, face by face. this has very important consequences, actually. But I don't want to go into the details. Maybe I would just mention a little bit more about that. Because basically, you know that there are links between the nodes, which means that if the state between, let's say, these two nodes, phase by phase, is maximally entangled, then we can say that these two phases are glued together, okay? By quantum entanglement, basically. I will say a little bit more about this because this is something important. But what then I'm going to compute, actually, is this amplitude. And this amplitude is a function of 5 intertwiner qubits. And this is a number which people in loop quantum gravity try to derive using classical machines. And at the end, actually, if you try to do it by hand, you will find that this is associated with the 15J symbol. You know, 6J, 3J symbols, okay, when you compose the spin, these are basically Clebsch-Gordan coefficients. But if you have the 5 spins and you combine them, I mean, this amplitude classically is proportional to 15J symbol, which is actually difficult to compute using classical computers. But then let me say, since I still have some time, let me say a little bit more about entanglement and colonomies. Actually, you can say that colonomies are mediating entanglement, because colonomy is actually a map from one Hilbert space to another. So you have some Hilbert space, the qubit, for instance, the Hilbert space at point A, and you have another Hilbert space at point B, and you have operator which maps a state from this Hilbert space to that Hilbert space. In loop quantum gravity, these colonomies are of this form. But then let me consider a simple example. Simplified version, I mean, along one direction. With sigma x operator here. Actually, the A is decomposed into the Pauli matrices. And then, in a simple case, you can decompose it in this way. This is for the purpose of illustrating the thing. Actually, this colonomy corresponds to the cosmological models when you have homogeneity and isotropy. And then in a special case, when you choose the factor alpha equal pi 2, you see that the colonomy is just x operator. X is a sigma x. So this is just a bit flip operator. So it means that your spin at this point is in the 0 state, then your spin at this point must be in the 1 state. So the colonomy actually maps states from this point into the states in another. Therefore, they introduce a certain kind of correlation between the particles, because actually this is a 2-particle state, and this is something very interesting. And the question is whether actually we can use the colonomies to encode entanglement in the similar way as we do using the tensor networks, okay? Because the tensor networks actually a geometric structure, graphs, which represent a structure of entanglement. So this is something I'm thinking about. I'm exploring this direction right now, but this is a side remark. And this might have also implication considering gravity entanglement duality, which ADS-CFT is an example of. But then let me go back to the object of our interest, the transition amplitude. For simplicity, I mean, we can get the transition amplitude, not only the absolute value square, but then we have to perform tomography of the state, actually, which is much more involving, okay, because you have to perform a lot of measurements. But now let me show you something simpler, I mean, to calculate the absolute value of this amplitude. For the pentagram. So if we have a pentagram, then we know that for every node we need 4 qubits, because every intertwiner qubit is encoded by 4 qubits, the basis qubits, I would say, the elementary qubits. Therefore, the register to evaluate this vertex amplitude requires 20 qubits, because 5 times 4 is 20. And then you start with some initial state, which is a product of 0 states for 20 qubits, like here. And then I wrote a very simple algorithm to derive this number. Namely, let's create the unitary operators u psi and uw such that those operators create psi and w state from the initial state of the quantum computer. And then you have to express somehow these operators in terms of elementary gates. And then create an operator u, which is the uw dagger times u psi. And then you can see that if you act with this operator on the initial state, you have some superposition of the basis states. For 20 qubits, your Hilbert space is 2 to the 20 dimensional, which is over 1 million, actually. The Hilbert space is over 1 million dimensional. And then look for the following thing. The action of the u operator on 0 state can be written like that, but u times sigma is 0. And acting with the bra on the left side, you see that A0, okay, the coefficient A0 is actually this transition amplitude. Therefore, the thing is that if you extract the probability of the initial state in the final state, so the A0 coefficient, you will find the scalar product. But of course, in the experiment, you don't measure A0, but you measure the probability, so the absolute value square, which gives you the absolute value square of this amplitude. So the task is the following: create these operators, write the u operator, act with this operator on initial state, perform the measurements, and extract this probability. And this probability gives you the answer, okay? This is something very simple conceptually, but then you see that if your basis is 1 million dimensional, extraction of the amplitude of a single basis state requires a huge number of measurements. Because at least to have a chance to get one measurement of given state, you need around 1 million measurements. Then to have a reasonable statistic for every of the basis state, you have to perform, I don't know, at least 10 millions, 10 million times the experiment, okay? So that's the problem, okay? The performing, executing quantum circuit is simple, but then extracting relevant information is time consuming. This is a simplified case of this, but let me already switch to the final one, which is the previous examples were just the warm-ups, but let me go to the pentagram diagram. So now we have to execute the amplitude, and we start with as an example, we start with the spin network, which is a product of the 5 basis states. So the first thing we have to do in our algorithm is that we create this side state using the u operator, And then after that, we act on the state with the dagger of the UW operator, okay? One after another. And then we have the operation U. So the first thing is that we create these states. So, and we consider the sets of 4 qubits. This is the first qubit. And this part creates the 0 S states for one intertwiner qubit. This guy, these 4 qubits, I would say elementary qubits, create the intertwiner state for the second. And the same, okay? So this part is an operator U psi. And then you have to act with the operator UW dagger, and the UW dagger, because, yeah, one more thing to make it clear. W state is nothing more than a product of 10 Bell states, okay, for every links. And all these epsilon L states are just the Bell states, and we know how to create the Bell states. We had the operator for the Bell states, but now we have to perform a dagger of that, okay? So it inverts the order, but because all the gates were unitary actually, okay, because X, Hadamard, and C nodes were unitary, it does not change the form of the gate. So it does change only the order in which the operations have to be performed. Therefore, you go now from the end. So you, let's say, these two, this C naught, together with this Hadamard and these two X, introduce entanglement between certain 2 nodes. But you act in the reversed order right now. So you instead of performing X, then Hadamard and C naught, you start with the C naught, then Hadamard, and twice X. Okay? This is because of the dagger. And then you have to glue together the nodes using the Bell states 10 times. Okay, so there are, in total here you have 10 operations which introduce entanglements between all the pairs. Okay, in the pentagram, and this operator is U psi times UW dagger. Okay, this quantum circuit represents this operator. And the thing is that at the end you have to perform the measurements, because you have to find the contribution to the final state from the initial state. Okay, and the thing is that of course you cannot do it with the 5-qubit quantum computers. With a 20-qubit quantum computer, even taking into account the limits of the topology of the processor, perhaps you can do it, but what I started with is that I used 20-qubit simulator of quantum computer, which is provided also by the IBM online. Okay, but the problem with this simulator is that there is limited precision of the simulator. So the precision is actually 1,000. Okay. And what I found from this first try is that the contribution from this probability is smaller than the precision of the simulator. But the thing is that there are much more accurate simulators, and you can do it to any, order basically. But I started with this simulator. Now I'm going to switch to something more. Something with much bigger precision, just to get actual numbers. That was, I would say, the first step. So I think with the simulators you can do concrete measurements of these amplitudes, not only for this one, But I'm going to right now, perform the amplitudes for the different states, generalizing this. And this is one of the tasks to do now. So let me a little bit summarize and give you some outlook. So, yeah, as I also mentioned, I extracted the amplitude modulus square, so I don't have information about the phase factor, which is important. Then to extract the phase, you must apply some other methods, in particular tomography, but there are also other algorithms like a phase estimation algorithm, which might be used to extract this phase. So this is something I'm working on currently. A lot can, even if the power, of the quantum computers, actual quantum computer is still limited, there's a lot that you can do with simulators. Okay, so simulators are accessible, and there's a lot of them. Some of them have much bigger, higher precision than the one that I used, and I'm going to go in this direction. And then ultimately, everything will be tested with simulators, and then quantum computers with 100 qubits will come, let's say in 5 years. Then we can switch to actual machines. Of course, I restricted myself to the certain kind of spin networks with all the spin labos equal 1/2, because these allowed me to introduce the qubits. But you can also think about the generalization to other sets. You can apply it to many different things actually in quantum gravity. Important thing is entanglement, because you may verify. In gravity we observe that the entropy entanglement actually scales with the area, like as for black holes, for instance. And one of the tasks is to verify whether this scaling might be extracted from the spin networks by measuring the von Neumann entropy between the two subsystems, and then you can well define the notion of the space, of the area between the two subsystems. What interests me a lot is the relation to the gauge gravity duality, because in this direction, instead of actually simulating gravitational degrees of freedom, you simulate some system on the boundary, and from the correlation you extract the information about the gravity system. And this is something what you can also think about implementing on quantum computers. There are new architectures emerging. So this is the 20 qubit ARI, which is provided by IBM. There's also another one, and this is the structure of interaction between the qubits for the 50 qubit quantum computer, which is developed. It has been built by IBM actually, but it's not available yet. They test it. And there's a Rigetti quantum computer that I mentioned, which actually use this kind of blocks, and then they combine them to the processor containing 128 qubits. This spring I mentioned you about, because primarily I also work on adiabatic quantum computers, which are also very interesting in the context of quantum gravity, and I'm still pushing forward this direction. And they have much more qubits, but they actually solve the classical problems. But just wanted to mention that meantime, there were very nice simulations performed using adiabatic quantum computers, namely the many-body systems, actually condensed matter physics systems were simulated using this D-wave quantum chips that I discussed last time. And they have shown nothing new actually with respect to what has been done using classical computers, but they prove that actually collective behaviors might be studied, and they extract the phase structures, etc. Of course, this is still the beginning, but I think this is something very promising, and we have to also think about this and look at the progress with this technology. Thank you.
Thank you very much.
Yes.
Like 2 pages before you were mentioning the U-dagger. or free?
Sorry, these are additional slides.
Yes, here. And that the order of these synods, these long ones, matter? Or
What matters is actually, I mean, this one. You have, you know, this is combinational problem actually. Okay, at the end it doesn't matter because of the symmetry. Okay, so you can order. I order them in such a way that for every intertwiner qubit I had two controlled and two controlled. Okay, so you see for this is a single qubit. So these two qubits controlled these two, but they were controlled by these two, okay? So I did it in a symmetric way, that for every qubit, intertwiner qubit, for every tetrahedra, I had this symmetry, so two qubits out of the four controlled other, and the other two were controlled by two other, okay? But you can do it in a different way, using all the permutations, you know, basically, okay?
And you mentioned that very important what kind of topology or architecture your chip has, and if there is no such combination of qubits that is required for building up a pentacolumn, then you cannot perform these measurements.
You mean, I mean, for the simulator, I used the simulator for that. So there were no constraints from the viewpoint of the topology of quantum process.
If you have a quantum computer, then if you have
Then the thing,
proper topology,
yeah, the thing is that, at least what I know for the moment, is that using the 5-qubit quantum computer, you can generate any state of the intertwiner qubit. Not only this particular one, not only the zero state, but also the other. This is a new. This has not been published, but I'm working on this currently. Okay, so you can generalize it to any other intertwiner state using actual, not a simulator, but quantum computer, 5-qubit quantum computer. But then, if it goes to the spin network, actually, if you just try to glue them together, then you would like to glue the nodes which are distant, okay? So therefore you need a high level of interconnectivity between these parts of side parts of the processor. But on the other hand, interesting topologies, which I'm going to actually study, are such that you have, this is your vertex, this is your node, and then this is another node, this is another node, this is another node, and then you entangle them, okay, using this Bell states. So therefore you have only nearest neighbor interaction, and therefore you introduce the Bell states only for the neighbors. So therefore this kind of topologies might be enough to encode these structures. So it looks a little bit like an Ising model, okay? So you have a pairs of spins which are bounded by Bell state, and then you at every point you project this states of this 4 spins into the 0 subspace. Okay, so this looks very similar to what people consider in condensed matter physics, I think. And just answering to your question once again, it might be possible to use it with this, perhaps with some tricks, but it might be possible.
Good question. You said that in your 20 qubit case, to get you can build that state, but to get to collect the data, you have to repeat the measurements
Many times.
a number of times, that also proportional to the 20, right? Or even more.
Yeah.
So if you had that 100 qubit computer, let's say, and you also wanted to collect the data, wouldn't you have to repeat the measurements a number of times that is
Yeah, more than the time of the universe. Okay, yeah, but of course it's like that. It's like that. But you don't always need the full information about the quantum state. If you need the full quantum state, okay, the tomography of the quantum state, then indeed. But it's not always the case. I mean, in the quantum algorithm, usually you perform only a finite number of measurements to extract relevant information, and therefore you can think about, I mean, for 5 qubits maybe it still will be possible to get the answer, but for more we have to forget about extracting the full information. Okay, something what instead we can do is that we create the state and then we perform certain measurements. Okay, I don't know, for instance, we can measure correlation between 2 other qubits depending on the distance, and we can extract the 2-point correlation function. Okay, so these are rather the types of measurements that we are interested in, and these kind of measurements can be performed in a much shorter number of measurements. Okay, at the end, I mean, I've discussed the vertex amplitude, but then the thing is that if you compute the vertex amplitude for a single vertex, then you can use this number as an elementary building block for much more complicated amplitudes, but you don't have to use quantum computers anymore. You just take this number and use this number, multiply it, add it, perform superpositions, okay, to calculate some more complicated transition amplitude. Okay, therefore I'm not going to measure actually transition amplitudes for graphs which more than 5 nodes. Okay, it's not necessary to do it, and it will be also at the same time too difficult to get because of the number of measurements that you have to perform.
So, just a comment. So I think you should distinguish between statistical errors, which are due to the fact that you didn't make enough shots, and the systematics errors, which are due to the fact that you are in fact measuring on a mixed state, which is due to decoherence.
That's true.
And the latter error, I think, performing your computation on a 100-qubit computer with millions of shots wouldn't help at all. So to do computations efficiently, you would need like even larger quantum computer with a robust quantum error correction.
Yeah, yes, scheme. Yeah, I didn't mention that, but that's true. Yeah.
Hardware is more like in thousands of qubits.
Perhaps, yeah.
The error rate has to be 10 to minus 4. So even the classical simulator cannot simulate quantum error correction. This IBM simulator.
So we are.
But the quantum IBM quantum simulator is not very, I would say, sophisticated one. Yeah.
But from what you said, I got the impression that the main source of error is not necessarily decoherence, but the imperfection of gates.
I think so. I think the imperfection of gates is the main source of error. I mean, and the propagation of the error. Okay, because if you look, for instance, at the let me go back to one of the previous slides. Yeah, this one. This is the result. These are error gates from September this year, where I performed these computations, and you know they were at the level of 10 to the minus 3. Okay. But we know that thereafter that the errors were much higher. Okay, the error gates for the single gates are at the level of 10 to the minus 3. But then if you introduce this error into the noisy gates one after another, this error propagate, further amplify, and if you have a sequence of, I don't know, 10 C nodes, the errors might be very significant, and if you don't have any error correction system, which should be there, I didn't apply it yet because it was too simple, but Perhaps for 5 qubits it's not such necessary, but you can think about this, and perhaps it will be necessary to apply it at some point. But yeah, this is propagating a lot.
Question. So, assuming everything is perfect, how many qubits do you think you would need to get to go beyond the same model to get any answer which people are actually asking?
I mean, this 20 qubit system is already something that people struggle with using classical methods. Okay, this is something because this vertex amplitude has been recently investigated by my colleagues in Marseille using the classical methods, and actually the thing is that let me go to this. Actually, this amplitude. Okay, this amplitude is proportional to the, as I mentioned, 15J symbol. Okay, one of the Clebsch Gordons, and actually, at least from what I know from my colleagues, is that there are numerical difficulties with extraction of this of these numbers. Okay, using the algorithm they used. Okay, therefore, already at this point, the quantum computers and the quantum algorithms are becoming useful. Okay, I'm not sure whether there are no other ways to get it. Okay, but at the moment, at least, the people who are skilled in doing numerics, they were not very happy with the results for this amplitude using the classical computers. Okay.
Two questions. Wouldn't it be possible to, let's say, decrease the errors by introducing some kind of white noise for these gates or for the whole measurements? Like, the decoherences actually can be treated as some kind of white noise of the whole.
Why you want to introduce some more? You wanna control the error by studying how to better understand the noise. Perhaps people are exploring this. I mean, I'm not an expert in this part of controlling the noise. Okay, not yet. I'm not yet there.
Can you imagine having some CDT-like calculation on?
Yeah, I thought about this. I thought about this that it would be nice to put CDT on quantum computer ultimately. Maybe starting from 1 + 1, when you have one-dimensional special part, and then you perform the evolution in time. You have transfer matrix, and perhaps this transfer matrix may be encoded using quantum circuits, quantum operators. So yeah.
Thank you, speaker, again.
Thank you very much.